Okay, perfect. Okay, cool. So I'll start my kind of like little bit of intro why we're here today, and who you guys are, and then what you're presenting. So this is a webinar that ibpsa-usa Research Committee holds once in every month that we try to. And thank you, Chenny and then Dr. Timurdon being here and presenting on how cities can plan the energy transition using urban building energy models. So Chenny is a PhD researcher in systems engineering and leads the Department of Energy at Atlas.io at the Environmental Systems Lab, Cornell University. And his work focuses on urban building energy modeling, urban digital twin, and scalable methods for evaluating buildings' retrofit and electrification strategies. Lee was trained as an architect, so he holds a degree, Bachelor of Architecture and Master of Architecture diploma from the Architectural Association in London. And Dr. Timurdon is an associate professor at Cornell, where he directs the Master of Architecture program and Environmental Systems Lab. And his research advances sustainable architecture and urbanism through educational programming and strategic work at the intersection of design, computational, building performance simulation, and geospatial analysis. So a couple of reminders: webinar will be recorded, which already started recording, and it will be available on YouTube to watch later. Everyone should be muted by default, and then we will have 40 minutes presentation, roughly 45 minutes in demo. And then Q&A will be at the end. You guys are welcome to put your questions to the chat, and then we will try to respond them after the presentation. And AIA credit will be applied to the ID that you guys provided at the registration if you did. This is for architectural credits. And if you have any questions, email admin@ibpsa.us. Just a quick reminder that SimBuild Conference 2026 registration is open, and it will be in May. So we're really excited, and then we would really appreciate if you guys consider coming in and being part of it. And then for this group of research committee, if you want to be part of it, please scan the QR codes and then join. And then events, ibpsa events, again on our website, ibpsa-usa. Now I am going to go ahead and stop sharing my screen, and then Dr. Dawn will be presenting their work. And thank you so much. I'm so excited to hear, I bet all attendees are.
Can you see the screen?
Yes, perfect.
Thank you so much for inviting us to this webinar. We're really excited, and thank you so much, Aishegul, for the introduction and again invitation and organizing everything here. So Chang and I will be presenting on how cities can plan the energy transition using UBEMs. We'll share a little bit about our research, and I want to kick it off maybe with a little bit of kind of motivate the things that motivate us. If you think about buildings, of course, there's a significant amount of carbon emissions attributed to operating buildings. And I'm including a few more things here like transportation, because I think this is just also an artifact of how we design cities and build cities. And so in the research lab, we really want to help architects and urban planners to consider environmental aspects to maybe mitigate some of these carbon emissions, create more energy efficient ways of or forms of living. And then, of course, on the right hand side, you see a map that and a postulation kind of come from the UN that says that we will be expecting 2 billion new urban dwellers and by 2060, and that means we will be doubling our building floor area in that time. And in the architecture lectures that I give, this is of course always an amazing moment for the architects because there's a lot of work ahead of us, and there's everyone will have something to do. But of course, at the same time, the this carbon footprint that buildings have, as if we continue as we do at the moment, is somewhat worrisome. And in particular, I think one of the things that's critical to note here is that a significant amount of the building stock that already exists will still be around in particular in kind of North America, in Europe, kind of mostly where the growth rates are a little small. So this kind of new construction will happen mostly in the global south. And so um, we as a research team, we create software tools that help visualize concerns that try to help in the design process really make good decisions, informed decisions using data-driven analysis tools, and that range across a wide topic from tools like energy and daylight simulation tools that have been commercialized coming out of research, but also things like view score, view analyses, visual privacy analysis, thermal comfort, visual comfort, up until kind of mobility analysis, microclimate simulation, and of course also urban energy modeling. So, in a sense, kind of these urban tools, what we are trying to do is kind of arrive at a point where we can, with simplicity and ease, do something like, let's say, build like a serious sim city moving forward. If you know that game from your childhood. Now I'm dating myself. Of course, all of this work is done by an amazing team of people who share the same interests and the same motivations in the research lab that I'm directing, called the Environmental Systems Lab, which is situated kind of, I think I would always say, somewhere between the architecture department and the engineering school at Cornell. There's a lot of cross-disciplinary engagement from systems engineering, like where Chang is doing his PhD across from to environmental engineering, computer science, and of course the planning and the architecture degrees here. And I also want to know, like, spend a second on like thanking all of the people that have funded and supported us in the past, ranging from gaming companies, because we use a lot of gaming technology in some of our simulations, to very serious institutions like the DOT or NYSADA, just to name a few of them. And so with that, I wanted to jump in and maybe kind of share a little bit the story of urban building energy modeling and how we started this work here in Cornell. This kind of idea around urban building energy modeling, of course, is not new. I worked on these things for my PhD when I was still when I was still at MIT, working with Christoph Reinhardt and his group, and of course. But it took a while to kind of like bring this to Ithaca and Cornell in a way. And the kind of moment when this happened was when Ithaca announced to be fully carbon neutral by 2030. And so they had put in legislation this very, very ambitious plan to be carbon neutral. And this was really, let's say, an idealistic move where this was kind of a postulation. It was we want to achieve this, but no one really knew how. And so we started kind of working together very closely with the city government to think about like, okay, what are the carbon emissions? Where are they coming from? What are the things that we could look into that would be important, or where could we help? And a portion of our research kind of focused on active mobility and electrified mobility. But of course, we also wanted to support with kind of energy supply modeling and so forth. Geothermal, solar is a part of it. And then lastly, the buildings, like upgrading building envelopes. What would the impact of that be? Upgrading systems, and then thinking about adaptive reuse and recycling and so forth. So Ithaca is a small town, like for those of you who don't know, in upstate New York. It's a beautiful place, very cold at the moment. Kind of this picture that you see here, heating dominated city, is very true. Covered in deep snow at the moment. It has an aging building stock. Of course, it's a university in college town, very because of Cornell and Ithaca College, very, very large student population. Um, but maybe more importantly, from a building energy modeling perspective, it's a fairly manageable kind of sized city. There are 5,000 buildings within the municipality, and that's just kind of the center, kind of City of Ithaca jurisdiction. And as we are zooming out, we're also working with the county. Tompkins County has about 20,000 or 25,000 buildings roughly um, under its purview. So we kind of had these conversations and were thinking, okay, how can we help the city first of all understand the building stock a little bit better? And so we sat with them and kind of tried to gather information about the building stock, everything that they shared openly everything that they had. We put together these kind of GIS workflows that cleaned up some of the data and kind of try to paint a picture of the building stock. So here, what you see, one of the key ingredients of if you are creating, let's say, a digital replica or twin or urban building energy model of a city, you would need the building footprints, you would need height information, you would need program information, like what is the building used for. And so this is a map showing this. We also scan through the permit data, and of course, that permit data um, is incredibly valuable in the sense that we know now for each and every building, has this building been upgraded? If it's has it been insulated? Has there been a window installation? Has there been photovoltaic installed or furnace upgrades happened over time? I wouldn't overemphasize the quality of the data. Sometimes it's very detailed and you know exactly the COP of the system that was installed. Sometimes it just says HVAC system installed. And so of course, this is really more like a pointer for us to help us make more educated guesses what's actually in the building. The other thing is the geometry, of course. This is where we really struggled a bit in the very beginning. So we were really interested in creating a accurate, very, very accurate digital replica of the building geometry. And this is, I think, in particular relevant if you think about energy consumption in buildings, where the windows are on buildings. That's always an unknown, usually. And so we investigated or invested a bit of time using kind of these photogrammetry created textured mesh models and building workflows that use computer vision and basic image segmentation methods to identify where on the envelope there are windows. And so this is kind of an ongoing research in terms of scaling this, but we have published two papers on this, and it's really an amazing technology in the sense that we can get really, really detailed building envelope information into our energy models. The other component, of course, is vegetation. Ithaca has lots of smaller buildings that actually are situated under thick tree cover. So, unlike some of the other urban energy modeling work that we are seeing in papers and conferences, where we are dealing with very large cities, very large buildings, um, uh, the where vegetation and terrain are mostly all of the time ignored. In Ithaca, that's something that we really thought would lead to a lot of modeling errors, and so we invested quite some time into building methodologies to process LiDAR data at its full extent in terms of detail. So here you see a representation of the LiDAR, like a LiDAR tile set, 15 by 15 kilometers, covering all of Ithaca, that has been classified into water features, vegetation features, and building returns. And then we voxelized this entire scene, and then built like a special kind of shading calculation methodology that's also just about to be published in the ibpsa journal, JBPS, so that then can give us sunlit fractions for any an arbitrary roof surface, or any arbitrary location on a roof, arbitrary location on a facade. And that allows us to create incredibly accurate kind of overshadowing calculations at this scale, taking into account vegetation and also the terrain in Ithaca is really, really important because there's steep slopes where the buildings are situated in, and basically there's like the city is kind of down in a canyon, kind of flanked by quite a hilly countryside on the sides. And so one of the things that you can get from this is a very, very detailed solar map that you see here that gives us kind of at a 50 centimeter resolution, basically the radiation potential on rooftops, but also on facades. Um, and that's kind of how just working with the geometry, we can build a replica of the city. And I want to hand it over to Cheng to talk a little bit about what when we have the geometry, how do we actually infer what's happening in the building? How do we obtain all of the input parameters that are required for creating an energy model of a building at an urban scale?
Thank you very much, Timo. So upon our survey, we realized that, okay, so the information that we can have in the openly accessible records, such as tax records, building permits of each of the individual buildings in the urban building energy model is really limited. We may have a very much rough or human crafted description of the heating cooling systems, almost no information about the siding or wall materials, some information of the air, some information about the area, a little bit of information about the hot water, etc. But these are really far away from what you need for a conventional urban building energy model input or any building energy model input. So that's why we need archetypes. Archetypes are preset definitions for how typical buildings are configured and how typical buildings behave in their building properties, etc. But we realized that there's a significant limitation in terms of how we design or conceptualize building archetypes. For example, the DOE building archetype, the BOE reference buildings for Energy Plus, they have, I couldn't really account for, but they have like more than 50 models for even one climate zone. They have one model for one, they have a specific model for one vintage, for one building types, etc. Meaning that a lot of information which are actually shared across all these buildings have been duplicated, and this creates unnecessary difficulty in how we assign building archetype and how we really use building archetypes. So in response to this challenge, we've been working on this research in this paper where we propose that we should separate the idea of a building archetype or template into the three distinct categories that are construction, energy loads, and conditioning systems. It is quite understandable that, okay, construction might be something that's highly related to the climate zone, but not that much varying across different building types, and it may also be related to building vintages. Whilst on the other hand, energy loads is entirely a, shall we say, choice of human. Its efficiency is related to vintage, of course, but it seldom varies across buildings in the same climate zone or buildings of different types even. And also conditioning systems, we presume that it is something that's very much very much tightly related to the occupants' behavior within these buildings, less related to any other attributes we can get from the urban perspective. So this stratification and this understanding of what typical building templates would comprise and how we could best describe these buildings has driven us to do a thorough analysis of what is available at a national scale. That's the Residential Energy Consumption Survey and the Commercial Building Energy Consumption Survey. They are two comprehensive reviews of all the stock level and the individual building level behavior of all buildings in America. And we've stratified these two surveys into the three categories. And after we have stratified the national survey into the three categories, the next challenge would be about how we should use these high fidelity, shall we say, survey data to inform building level energy model inputs. So that brings us to the next slide of a shall we say, machine learning data-driven workflow of how we should fuse these two data sets at very different scales. On the right hand, we have the national survey data. On the left hand, we have a little bit of information about each of the buildings. So we have clustered the national data set, derived the typical archetypes, and trained machine learning models to infer the archetype assignment based on, I call them, the non-attributes at the building level. So go to the next slide. So this slide summarizes what are all the archetypes that are at work at this climate zone 6A, when will also be the archetypes being assigned to the buildings. We see that we've stratified archetypes across different building typology categories for the residential sector. For construction archetypes, for system archetypes, we have this number of archetypes per housing typology. But we've deliberately made the decision that there's no need of such stratifying energy loads in different housing typologies, because we believe that the occupant's behavior is the main driver behind the energy loads, and they seldom vary across different building typologies. And you see that we have definitive qualitative or nominative values for different construction systems archetypes. For example, we see the standard linear window mobile home, which will have a typical U value, typical heat gain coefficient for this specific climate region of America. However, we argue, or we find out that for energy loads archetypes, or specifically for the electric equipment power densities, gas equipment power densities, water heating power densities, etc., it's very difficult to give a definitive fixed value estimate. And it's quite a limiting approach to do this. So we are arguing that we need to characterize these buildings by not a specific fixed input for the equipment power density, etc., for buildings, but a distribution or empirical distribution driven spread of possible values and their probabilities, so that we can further take account of this spread of confidence in our future calibration and validation workflow. Maybe next slide. However, so these national surveys and national statistics and these archetypes driven from these statistics, they may perform very good at inferring the, qualitative attributes and qualitative inputs for the buildings, such as the properties, the U values, the system archetypes, vintages, etc. However, they inform almost nothing about the schedules. So which energy loads should happen at what time of the day or what time of the year still remains something that's beyond our knowledge. In fact, that in most energy models or urban building energy models that we are handling with, they assume a fixed schedule across all households or buildings within the same group, meaning that, okay, if you have a occupant schedule of a peak load or electricity use peak at say 8 a.m. in the morning, everyone is making breakfast, and all the occupants in this region will be performing the same behavior at the same time, creating these sort of fake or artificial peaks that actually don't reflect the actual electricity use patterns. So that's one limitation in the building archetype approach we had. And we are working on this paper, which is under review for SimBuild 2026, so another invitation to attend this conference, and we can discuss ideas there about how we can better predict the hourly loads for urban building energy models. It has been traditionally believed that urban building energy models, due to its low fidelity and reduced order assumptions, was never capable of doing such highly fine-grained temporal predictions. But actually, we argue that with a definitive, with a limited number of diversity in the schedule archetypes that you had for the inputs, you will be able to kind of mimicry the hourly load performance at the building group level, and to a very much acceptable accuracy. This is also thanks to our utility partner Avangrid and NYSERDA, who was generous enough to provide to share their data set on all the address level energy consumption data hourly for the entire year of 2024, which made this validation of this advancement in urban building energy modeling archetype methodology possible.
Great. And of course, that's one of those kind of things that I think the utilities, when it comes to urban energy modeling, are really interested in, because with the thermal load electrification kind of shifting from gas furnaces to heat pumps, as well as the vehicles that all of a sudden also plug into the homes for charging, there are significant concerns around like the safety of the grid, capacity of the grid. So understanding the peak loads and being able to forecast that with the changes in the building stock is of an incredible importance to them. And so this is kind of a really exciting thing that we would love to see, that we can actually leverage some of these UBEM models to kind of do this peak load forecasting and planning, and help kind of with the energy transition in that way. So what we talked about is basically thus far is really about like this data gathering and data fusion exercise. And so this is kind of, this slide kind of summarizes this workflow maybe one more time. So we have a plethora of GIS data layers that we can extract useful information for, to get a better sense of what's happening in a building, how is the building made, how large is it, and how is it overshadowed. And so we have this geometric pathway at the top, and then at the bottom we're kind of working on, let's say, all the non-geometric properties that describe a building, where we are using kind of indicators or features in the GIS data to then extrapolate, like on the kind of internal workings on, let's say, the space use and energy usage profiles, the systems that are being used that are installed in the building, as well as kind of typical, like drawing from a catalog of typical constructions that we then assign to a building. And so as we are fusing this all together, we are creating basically a unique energy model, building energy model for every building in the city, using the geometry, and then joining that together with the non-geometric data. And that can then be passed into a simulation engine. For example, we can pass this and build like a full Energy Plus model out of this with this information. But we've also spent some time and developed much faster lower order simulation models, like the the very popular 5R1C models, for example, that can be used to kind of simulate buildings accurately and quickly. And so once we have these kind of models, the thing that's missing is, of course, the weather data. Here we are drawing from databases from NREL, where you can download historic weather data for all of the US for several years back. And then, of course, that's relevant when it comes to validation of the model. Of course, we want to validate against with using the correct weather data. And then when it's coming to scenario simulations, we tend to use like typical meteorological year weather data, sometimes also morphed future weather data or extreme weather data, depending on what the scenario is. So this is kind of completely interchangeable, and then you just run the simulation again. I should say the computational overhead for this is actually fairly small. So um, if we were to do this in Energy Plus, of course, this would take a while. But with our own lower order model, I can run kind of the City of Ithaca on my laptop computer in under 2 minutes, like 5,000 buildings under 2 minutes. And I should say, this is not a surrogate model or an AI driven model. It's just a simpler kind of representation, a lower order energy model, but it's still physics based and fairly accurate in this kind of scenario of UBEM. And then we can use these models once we have our what we call a baseline model. Of course, you can kind of test different things, change inputs, swap the HVAC systems out, and so forth. And then you get results that you can then also combine with other models, like for example, techno-economic models that will share some results on how we did this in Ithaca. And so if you have all of this, this is where you end up an energy model of the city of Ithaca here, showing kind of energy use intensity mapped onto the buildings. And now, one of the key steps here is, of course, accuracy. And as I already mentioned, is like we are putting together all these data sets, and we call this kind of our best guess assumption that we start with. And then if you have validation data at a building level or at a block level, you can then kind of first of all, check how accurate is your initial assumption. And then, of course, if you know which parameters of the building models are somewhat uncertain, you can then use calibration techniques or strategies. And in our case, we used a very simple strategy, actually, using a Bobiqua optimization algorithm that gets a few of these uncertain parameters for calibration. It's constrained in the sense that we only allow it to change the values in a plausible range, and this is what Cheng had alluded to, that we use the survey data to kind of infer what for a building of this age and size, what is a plausible range, let's say, for example, for the facade U value or for the infiltration rate or the equipment power density. So these are the three, and you see in these histograms, these three main uncertain parameters in our building models. And then you see kind of in the histogram, the initial guess is always this like big blue line. It's like one parameter that's been assigned to many buildings in the model. And then we start this calibration process where we validate or try to test our accuracy against, in this case, was monthly metered data, monthly build data or monthly building data from the utility shared for every building, where we then compared against kind of a winter error for gas and electricity, of course, and a summer error in both of those cases, and try to kind of match, let's say, the peaks and the valleys we wanted to get really we wanted to get right. And when you do that, the calibration kind of then starts to spread out some of these parameters and creates kind of the gray distribution, let's say, of these three uncertain parameters within the modeling domain. If you look at the overall accuracy of this, then here in green, you basically see the histogram of electricity consumption in the city. Green is our initial guess. The billing looks a little bit different, which is the navy blue. And then as we start with the calibration process, we kind of slowly basically push these curves closer to each other or on top of each other, these histogram distribution curves. And the electricity consumption is actually, I think, maybe the weirdest one, the one that is like the initial guess is most off in a sense. But it's not like orders of magnitudes different. It's a fair assumption, a fair guess. And with the gas consumption, which is much more climate driven or weather driven, the initial guess is even better. And as we calibrate, then get a very good match. Now, this is, of course, kind of showing it kind of at the zoomed out level as a histogram for all buildings in the modeling domain. So a little bit kind of like blanketing the errors that maybe happen at the individual building levels. And this is of course, not magic in the sense there are some pretty significant errors at the building level that we're seeing for some buildings, but for the majority of buildings, we get a very good match. And we try to kind of then kind of pinpoint what are the buildings that we really struggle with modeling, and it's buildings that, for example, are actually vacant, and we assign a program to them because that's still in the GIS data, and of course then it doesn't match with the building data at all. And there's quite some buildings of that character within the Ithaca modeling domain. And then there are special buildings or atypical buildings, student dormitories, or with cafeterias in them and so forth, large cafeterias in them, buildings that have a mixed use in terms of commercial floors that then have very high density housing on top in College Town in this case, that we don't represent well with the input templates because they are kind of underrepresented in these kind of archetype or building consumption surveys. Or other buildings like special buildings like the wastewater treatment plant, the bus depot, those buildings we really struggle modeling correctly. And of course, that's an ongoing process in refining that moving forward. Now, with the kind of baseline model validated and calibrated, we come to the moment where we actually can play with the model and test scenarios. So for the City of Ithaca, we did kind of lay out 5 very, very simple scenarios. We said, okay, here's your baseline energy consumption. That's the first bar that you see. Then we checked, okay, at the gross level, that checks out with kind of what the city has been calculating in terms of overall building operational energy use. Now, what if we changed all of the gas-based equipment in buildings and electrified it? That was one of the questions. And I think this was kind of how the city approached its carbon neutrality goal. It's like electrify, electrify, electrify. And that's the first scenario. And we basically just assume that everyone does it. Everyone will do this change. And then you can see how this basically can cut down the energy consumption of the city almost in half. And then we tried other scenarios where we, again, very aggressively or kind of let's say naively approach this and say, okay, what if we took every building that has a building envelope that is not up to code, and we made it up to code of the new building energy code that Ithaca has currently. So it's a very kind of, let's say, upper bound scenario, and you see that's the scenario 2 that you see here. And then in combination, that's scenario 3, we basically combine the first 2 scenarios and add them there. And then we kind of mix up these scenarios that I just mentioned with installing photovoltaics, right? So electrification and photovoltaics is one pair, and then the full envelope upgrade plus electrification in PV. So this is kind of, let's say, the upper bound of what's possible in Ithaca would be scenario 5. And you see from a carbon emissions perspective, of course, but simply doing the electrification is already putting a big dent in carbon emissions, because upstate New York has a very clean grid, or much cleaner grid than the rest of the country, I should say. And you get a 70% reduction in carbon emissions from the electrification alone. But we're nowhere near net zero unless we bring building integrated photovoltaics into the mix here when we do this modeling. And we were just interested in understanding, like, how feasible is this really? How close can we get? And we can't really match this with building integrated photovoltaics alone, but you can get, let's say, you can get close to carbon neutrality with this. And of course, Ithaca has other resources like hydropower and other renewable power, like renewable energy power plants in the vicinity, like voltaics and so forth, that are also an option. So I think this was kind of the good news, was this idea of becoming carbon neutral in Ithaca is very feasible. But of course, the big question that remains is cost. And now I'm going to pass it on to Cheng to talk a bit about that.
Thank you, Timur. So we've been analyzing the breaking down of the cost, not only in terms of how they are comprised of, from the nature of the cost perspective, how much money is spent into the retrofit of which sector of the buildings, but also we are looking into the fact that if each building can be modeled to be eligible for certain federal incentives, state incentives, and other tax rebates, etc., to further offset the initial upfront cost, so that the financial case for each building level retrofit program would be made even more feasible. There are some interesting, findings in this regard. For example, if you look at the colors on so we're looking at the right bar of each of the scenarios, and we're looking at the bottom 2 colors, which represent the total amount of federal and state incentives available under this retrofit scenario for all buildings, we've seen that the state level incentive had a somehow improportional increase across the scenarios 3 and 5 compared with others. The reason behind this, when we dig into it, is very interesting. We've seen that when we combine envelope and electrification and envelope and electrification and PVs, we are unlocking more state level incentives. And the reason behind that, if is on the next slide, is because we've modeled this specific New York State clean heat program, which somehow it in itself incentivizes installation of all sorts of heat pumps as a, shall we say, as a measure to phase out the fossil fuel energy used to heat the spaces and buildings. And its, shall we say, eligibility criteria of incentives is very much tied to the total energy saved percentage. So if we only electrify buildings, we are not actually saving energy because you need almost the same amount of energy, if not more, to heat the space to the same level of thermal satisfaction. However, if we install envelopes and when under this and only under this scenario, when we install heat pumps, etc., we'll be eligible for this clean heat program that will evaluate the amount of aid or amount of incentives or tax rebates or purchase rebates eligible according to the total energy saved percentage.
And this you're referring to, you're not saving money, right? Like you're saving energy, but you're saving money.
Yes.
Yeah. Mm-hmm. You're not saving any money if you just electrify in some cases. Yeah, and so with this modeling, I think what was key then is to kind of say, well, to the city, can we, from this kind of, let's say, top-down perspective of modeling, how can we now make this a reality? I think we need to start targeting buildings. We need to figure out who to talk with in terms of building owners and convince them that these retrofits are a good idea. And so we were really interested in kind of pinpointing where the lowest hanging fruits are in the city. And we did that by defining a benefit cost ratio, very simple approach, kind of saying we are interested in the carbon emissions reduced by the amount of dollars spent for the upfront investment, and then of course also over the 15 years of operation. And so this is kind of now this analysis stretched out over 15 years to understand which buildings could benefit most from quick retrofits, including the incentives and so forth. And it was quite interesting how that then kind of lined up buildings in the chart below. There were a few buildings where we always said retrofitting is almost for free because they are eligible for a significant amount of incentives falling into category A, which is large-scale multifamily in low-income neighborhoods. And so this is quite a significant chunk where you get very, very high benefit with little cost to the actual owner. And so these would be properties to reach and target, to reach out, engage with at the very beginning. There's some large-scale commercial buildings, which is the kind of group in red, the B group, that also would have a significant kind of favorable benefit cost ratio. Then again, large-scale multifamily, and then a significant chunk of these kind of like single-family homes. And with this kind of sorting or ranking, we provide some guidance on like how the city could really kind of begin and make this a movement within the city and kind of convince the building owners to do this kind of modeling. And Chang has a few more details here.
Mm-hmm. Thanks for handing over, Timur. So in addition to the upfront cost or whatever money you pay to buy the equipment or buy the envelope, the actual, shall we say, financial argument that directly affects the feasibility of such retrofit is related to the, shall we say, return or the return of investment or any other similar financial indices. So we looked into the fact that any shall we say, energy retrofit or any building retrofit would necessarily result in some sort of savings on operational energy usage, which results in the savings on the electricity bills, gas bills, etc., etc. In the 5 scenarios, we've tested out the preset payback and the preset payback index of 20%. And so the number of buildings who will be eligible, who will be possible to achieve such who will be possible to achieve such payback under the different, shall we say, scenarios and their years taken to achieve such paybacks. So if we look at the first scenario, what we'll see on the first row of this plot is that almost no residential buildings will be able to pay back the initial investment in air source heat pumps or as such because of the sheer, shall we say, cost of installing such equipment on the one hand, and also on the other hand, the cost of gas and natural gas in the northeastern United States is really is not that expensive. It's actually very cheap source of energy. So switching to electricity actually doesn't really help you saving your bills. It's not very much attractive business case to state in this occasion. However, we still see buildings that could qualify for under 12.5 years payback of 20% for residential sector. These are buildings that are mainly student accommodations or multifamily buildings. These buildings, shall we say, they benefit a lot from air source heat pump upgrades, and even without a envelope retrofit or envelope upgrade.
So one thing to add here, one thing to add here is kind of, I think what the city of Ithaca is now using this information to negotiate a special heat pump tariff, for example. And so this is another one of those examples how this kind of data-driven approach to this decarbonization agenda is helpful, kind of giving kind of arguments to the city officials to kind of talk to the right people and communicate.
For the fifth, the most ideal, most deep retrofit scenario where we combine envelope upgrades in electrification and PV, we're seeing that most of the building will pay back sometime within the next 30 years or so. There are no buildings that wouldn't pay back, but you're seeing that even for the commercial sector, this is the only scenario where most of the buildings will pay back within 5 years, and I'll give you information that 5 years is actually their benchmark for looking at retrofit solutions. So what makes it different that all the other scenarios fail to let the commercial sector pay back within 5 years, while this scenario does? The reason behind that is, in a way, simple. Most commercial buildings feature with flat roofs, very much access to the PVs, and great potentials for building integrated PV installations that will offset a lot of extra electricity consumption introduced by the electrification of the building equipment. However, actually, we find that what is interesting here is not which buildings will pay back, but the buildings that wouldn't even pay back under this very aggressive scenario. And we've identified them as the two groups. First is that the tree-shaded single-family homes, their inaccessibility to solar radiation or inaccessibility to PV, potential PV generation, really limits their ability to be self-sufficient and to the ability to generate enough energy to offset their extra electricity bills introduced by the electrification program. The other one are the downtown mixed-use buildings. They feature with high energy use and also the limitation of access to the solar radiation because of mutual shading and other geometry-related factors. And talking about solar, about building integrated PV simulations, we actually had some interesting findings in this sector as well. For example, if we compare the sector-wide PV potential, that is to say, if we just install PV in all eligible locations and compare the actual generated energy of all the PVs installed and the sector-wide energy consumption, they are balancing out very much for the commercial sector, and they are quite close to balancing out each other for the residential sector. And I can explain the streets or the orange bars, the differences. So PV potential generation, we can install PV literally anywhere you want, but you only install PV on locations with great access to the sun and great actual annual generation potential. And we set benchmarks to allow the installation of PV or disallow the installations of PV. This 1,300 kilowatts per year benchmarking means that we only install PV on locations with 1,300 or more kilowatts per year annual generation. and etc. etc. So actually, the less like yellow or the less orange bar is the most aggressive PV scenario, and the highly saturated orange bar is the most moderate or sorry, I was saying this wrong. So the less orange bar is the most lenient or moderate PV scenario, where you only install PV on the absolute good locations, and the saturated orange bars are the really already aggressive PV scenarios where you install PV literally everywhere that's feasible. However, there's another side of this picture, which is that if we look at the individual building level self-sufficiency, meaning that whether your building will be able to generate enough energy for your electricity consumption, the result is very, should I say, discouraging. We see that like under any of the, shall we say, aggressive or non-aggressive PV adoption or PV penetration scenarios, like only like at most half of the building stock will be able to generate enough energy for its own consumption. Half the buildings will have little access to sun or have other factors that will impale their ability to be self-sufficient. That means the ability to generate enough energy for their own consumption. This raises the question of the concern of like the concern of, shall I say, the current policy, the incentive structure finances a injustice or unequal, shall we say, possibility of purchasing new or installing new building rooftop PVs to offset energy bills. And this is, shall we say, talking about this, how the cities should move forward, how cities should design incentive to facilitate integration of PV in the building sector. This is not the right way to move forward. Simulating and installing and hypothesizing building rooftop PVs is not enough. We need to look into other like less costly and also more feasible and more equal approaches, such as community PV or even utility scale PVs for small scale cities like this. We have plenty of land, rural, agricultural, and vacant for that could be great locations for solar farms. And also it is possible to look into, shall I say, solutions of installing PVs on top of parking lots and other sites of similar quality, so that we can take advantage of the possibility of sex-wide balancing without actually having to discriminate buildings without access to sun.
All right, I think we want to show you, we are close to time, but we want to show you one more thing. And of course, we are interested in understanding how can we scale what we have done in Ithaca, how can this be done in other places? And so we want to introduce to you a tool called Energy Atlas that is really kind of, I think, a user interface that aims to make this kind of energy modeling analysis easy, accessible, and hopefully it's not the energy modelers who will drive this in the end. We really would like to see some of the policymakers and city officials to tinker with this, or even kind of hand it off to some of the utility planning groups to leverage something like this. And Cheng will share a little bit more about the workflow of this new tool.
So we devised, we've broken down the energy modeling or urban building energy modeling task into 4 phases: integration of data, archetypes, baseline simulation, calibration, as well as retrofit scenario design and simulation. So I'll show you demos of all these stages and how Energy Atlas would be the best tool to support you, whichever role you are in this entire life cycle of of UBEMs. So the first stage is integration of urban data. Don't worry, I'll show live demos afterwards. We have developed this tool to download overture maps that contains globally available building footprints and attributes, as well as we crafted a AMY, that's actual meteorological year weather downloader that's available or open source online. It will fetch national radiation database weather data for you, so you can simulate anywhere, any year. And we've developed this archetype assignment logic. We know that archetype assignment is daunting, and with lots of new concepts and lots of complicated things happening here, we've wanted to make it simple, and we made it. In the archetype assignment portal we have in the software, we've designed a simple combination of rules and archetypes. You can specify any rule you want through like the logic, the conditions. You can add any condition you want. and you can assign archetype based on this. We realize that modelers often struggle to, shall we say, represent their assignment logic, and even if they really spend the time to craft the logic, there's no way to validate whether the assignment logic is doing the thing that they would like it to do, or they are making some hidden mistakes where no one would realize what the archetype assignment is doing. So we made this tool. The next step is based on simulations. We have this tool to allow you to simulate the baseline model with the inputs you have, and if you have validation data, to validate and produce the validation results and visualize validation results. And finally, we have this retrofit scenario designer. Similar as the template assignment tool, we have the selection logic and the measures applied. For each measure, you'll be able to customize the measure, custom everything in the measure to specify any envelope upgrade you have, etc. These are abstract, but I'll show you the live demo of this software. Timo, would you be able to start sharing so that I can share the screen?
Yep.
Okay. I trust you're seeing some browser page, do you? Okay. So first of all, the building downloads or the integration of the data over to maps. It's taunting to download. It's in some obscure GeoParquet manner. No one will be able to understand that, or you don't need a specialty to understand that in order to use it. We made this tool so that you can download anything, anywhere related to building or relating to UBEM. So it has global tie availability, but let's just zoom in into Ithaca. We know about the city so well that we can ensure that nothing weird is happening here. So we zoom into Ithaca. We see that when we zoom in, the tiles immediately turns into building footprints. Please turn. Okay. And we pull up the places. We pull up everything. Okay, let's say we select a region, and we'll be able to download the GeoJSON for that region as one shot. So the loading was a bit small because my computer is really jammed up with all the stuff. But simple as that. Zoom in, select region like you do on Google Maps. And you get a GeoJSON loaded into Visual Studio. Yeah, and next step would be visualizing the data. So we've designed this like almost GIS, but you don't have to install anything tool. We can visualize any sort of commonly available feature types. I can toggle the layers. We can customly styling it. For example, this one I'm styling on something that's the heating fuel. You see that the heating fuel is beautifully mapped according to the legend of any choice you want. And you can even have 3D building geometries. I wouldn't show you, but you can participate in the survey. We'll send you a link and we can talk about this. Next, the key step, the template assignment tool. So because we understand how difficult it is and how daunting it would be to assign templates, we've designed to be simple and visual. So we specify rules. For example, I specify in this one a footprint area smaller than 100 gets assigned these archetypes, which I load from a repository or from a local file. You'll get this assignment tool of the highest priority. You also get other assignment rules of different priorities as your liking, and different selection logic as your liking, and you may even specify a fallback rule that will apply regardlessly, but has the lowest priority, so it will kick in only if everything else fails. You'll be able to see which building gets assigned which construction archetype. It's really slow. I almost saw the footprint loading, but okay, let's zoom out. You'll be able to see which building is assigned which type for the systems load as well, for the energy loads, and for the external loads. They should be switching and already even visualizing more what is happening in terms of which type of building is get assigned to which specific heating systems, cooling systems type, or construction archetype, etc., etc. For the scenario definition, the scenario designer, same logic. We have a list of measure packages, which we define as a combination of a selection criteria and assignment of different measures. Each measure package will contain a finite, a group of measures to be assigned. For example, for this one, I call it it's residential, so retrofit. For all buildings that are residential, I assign them this residential upgrade to IECC code, and maybe heating system measure, I'll upgrade into heat pumps. Cooling, I don't care. This is not a cooling-dominated city. hot water, I assign something, you can assign anything you want. You'll be able to switch and see different choice assignments, and they're broken down on the same key chart on the right as well, similar as you have for template. But trust me, this is a computer with limited computational capability. You'll be able to use it as if it's like it's smooth as you can imagine. And we would able to be we'll be able to be like the last bit. We'll be able to be we'll be able to be editing these, shall we say, rules or these measures as well. For example, if I open up this, shall we say, residential upgrades to IECC climate zone 6, it sounds very abstract. You don't know what is happening there. You click edit, you pull up the, shall we say, editing, shall we say, panel. You can edit the naming. You can, shall we say, input the fields, costing, etc. And it can also error check for you. For example, for the glazing, we accidentally input something that's invalid. For the heat gain coefficient, we have something that's more than 1, 2. It says, okay, it should be less than 1. It will like dumb proof or like this input so that it gets you what you like really wanted, and save it, update it, everything. You can export everything as JSON. You don't have to like have this one shipped or like running in your computer. You can close it, have a coffee, then go back and then work on the same material. So that's the gist of our Energy Atlas tool. We wanted, and we are doing this to simplify the UBEM workflow. We are making it accessible than ever so that anyone with any specialty can be able to use this tool without the need to install any additional software, without the need to, shall I say, learn how to model in Rhino, or how to, shall I say, go through all the like hundreds of fields in Energy Atlas, in Energy Plus, or like download the notches with all the IT permissions and other screening to install the software only to load a GeoJSON file or something. We understand your difficulties, we understand the challenges in this industry. We're doing this tool to relieve you of all of them. To wrap up,
Thanks,
this
Cheng.
tool is not. Oh, yeah, maybe you
Thank you
can
so
take
much,
over
Cheng.
and thank you.
This was meant to be really like a sneak preview of what's coming ahead. If you want to stay in touch, there's the QR code. You can also go to the website. And of course, we're here to take questions. And if there are any in the chat, I can't see the chat. So maybe if someone from the ibpsa team could read them.
Yeah, of course.
Yeah.
Yeah, we have a question from Kate. It's, have you run into any privacy concerns associated with studying customers' utility data to then using your findings to target those customers for decarbonization upgrades?
Yeah, very good question. This, of course, is highly sensitive topic. The data that we are using to validate the models and calibrate the models is, of course, under strict NDAs, cannot be shared publicly. And of course, the targeting is something that the utility does in conjunction with the city. So they are kind of managing this community engagement and handling all the privacy related concerns. But it's a very great topic to discuss, like how UBEM can be used without violating anyone's privacies. Yeah.
Awesome. And then the next question is, would those papers by this team, as cited in the presentation, be available?
Yes, they should all be available. If they're not, feel free to email us and we'll share them with you. Yeah.
Awesome. And those are all the questions that we have time for today. Thank you so much, everybody, for joining us. Thank you so much to our presenters. We really appreciate the time that they have taken to share their expertise and insight with us. As on the screen, make sure to fill out the survey if they're interested in testing Energy Atlas. And if you are attending the ASHRAE conference this weekend, make sure to get tickets to our semi-annual event happening on Sunday, February 1st. And yeah, thank you so much, everybody, for being here. Have a wonderful rest of your day and a good weekend.
Thank you. Bye-bye.
Thank you. Bye bye.